In this lesson, 2.6, you will learn how to graph absolute value equations. The big idea here is that absolute value equations can be easily graphed by shifting the graph of y equals absolute value x, and I'm going to show you how to do that. So let's look at translations. Shifts are called translations. Translations can shift a graph vertically, horizontally, or both. Look at these two graphs. These are graphs of absolute value equations. Notice that they are V's. So how are these graphs related? Pause the video for a second and think to yourself how they are related. Okay, and then when you come back, I want you to also consider how they are different. So if we look at these two graphs, we could probably take this V, cut it out, and put it on this other V. So they're the same shape, the same size, only this V over here on the right has been shifted down 2 spots versus this one, which starts here at 0, 0. This is the vertex. In this graph, the vertex is down, shifted down 2 units. Okay, and that's what we call a shift. So now let's talk about the family of functions so we can understand how the shifts affect our parent function. So a family of functions is a group of functions with common characteristics. The parent function for each of these families is the function that is the most simplest, in the simplest form. So there's a chart down here for you to look at. We have 2 different types of functions. You have a lot of experience with a linear function. The parent function is just y equals x. Right? If you look at this, the slope, which is in front of x, which tells us how much y changes for every x, is just 1. If we add a translation to that, that's when we have plus b, whatever the y-intercept is. And if you think about what that does, that shifts our linear equation either up or perhaps down. Compare that to an absolute value equation. The parent function actually looks very similar to the parent function of a linear function. It's still y equals, but it's absolute value x. So we have these absolute value bars. We have 2 translations that we can put onto an absolute value equation. We have an h inside of the absolute value bars, and then we have a k, which is on the outside. And the k is a common characteristic to the b in a linear equation. So think about what that does. Think in your head what that might do. Make a prediction, and then we'll look at it. Let's explore our parent functions for a minute. So if I were to graph these, there's many ways you can graph this. The first way that you are most familiar with is probably picking out the slope, which is 1, and the y-intercept, which is 0, and then starting from the y-intercept and going up 1 over 1, up 1 over 1. Another way that maybe you remember from some time ago is make a table of values, right? And you can pick any value you want for x. That's our independent variable. And it's best to start with a -1, maybe, right? Get 1 on each side of 0. And then I'll choose 0. And then I'll choose 1. And the way that the table works is we just take these values, plug them into our equation. So if we plug in a -1 for x, well, y is going to be the same. If we plug in a 0 for x, y is also then going to be 0. And if we plug in a 1, y is going to be 1. If I were to graph these, I would go out for my first point here, -1 on x, and down -1 and put my point there. 0, 0 is right here. And then over 1 and up 1 is my next point. So now I have graphed my parent function. I can go ahead and draw my line. And this is what the parent function will always look like. Okay, and we're going to compare that to the parent function of our absolute value function, y equals absolute value x. So we'll do the same thing. We'll go ahead and we will come up with some key points. And again, just like we did before, it makes sense to come up with some negatives. So maybe we'll do -1. and then some positives, and also 0, so we can see what our y-intercept is. If I put a -1 in here for x, well, the absolute value of any negative number is always going to be a positive number, so that will be 1. If I put a 0 in there, that's 0, and if I put a 1 in there, that's 1. Now let's see what kind of graph this makes. So for the first point, we have a -1 and an up 1. We're right here. Okay, and then my second point is 0, 0. That looks familiar. And my third point is over 1, up 1. Okay, and if I look at what kind of line this is going to make, you can see that it looks like we'll have a V, right? We'll start here at the vertex, we'll go up, once again start there at the vertex, and we'll go up to the left. Okay, and that is our absolute value equation. So let's compare the two, because we said there were common characteristics. Well, if we notice that in this absolute value equation, our vertex, and I'll go ahead and write that out, our vertex, and that's the point where the two lines meet, is at 0, 0. Okay. If I look over here, you'll notice that this line goes through 0, 0. In fact, that's our y-intercept, right? So in this graph, our y-intercept is actually 0, 0 as well. Another important common characteristic is look at our slope. If we start at our vertex, which is our y-intercept here, and we go up 1 over 1, we have a point, right? We could go up 1 over 1, make another point, up 1 over 1, make another point. Let's look at the slope of our linear equation. So if I start here at the y-intercept and I go up 1 over 1, here's my point on the graph. I can go up 1 over 1 again, and I have another point. So my slopes are the same. And notice in front of our x's, there's nothing there, so it's understood to be 1. So our slopes are both 1, our y-intercepts are both 0, and our vertex here is at 0, 0. Okay, let's go ahead and look at some translations. So remember that translations are just shifts. So let's take this first graph, and again, let's go ahead and make some points. We'll do it that way. So I'll go ahead and plug in the same x-coordinate points, just so we can see what happens. So if I put a -1 in here for x, -1 plus 2 is just 1. 0 plus 2 is 2. And 1, if I plug it in here for x, plus 2 is going to give me 3. Plotting these points, I get a point here at -1, 1, 0, 2, and 1, 3 up here. Let's draw our line so we can see what that looks like. Okay, here we have our new equation that has been translated. So let's think about what our parent function looked like. So our parent function went right through 0, 0, if you remember. Our y-intercept was at 0, 0. Look where our y-intercept is now. If I write that in our graph here, our y-intercept is at 0, 2. So look at what this 2 did up here. It translated our graph 2 units up. So can you make a prediction in this absolute value equation what this 2 is going to do to our vertex, or in other words, our y-intercept? So let's make some points just like we did before. We'll use our -1, 0, and 1 so we can see exactly what it does to our original graph. So remember, plugging in a -1 here for absolute value x just gives us 1, and 1 plus 2 is 3. Okay, plugging in a 0, we would have 0 plus 2, which is 2, and plugging in a 1, we would have 1 plus 2, which is also positive 3. Okay, so if we graph those, we're going to go out -1, up 3. We have a point here at 0, 2, and then another point here at 1, 3. Okay, let's draw our line. So again, our vertex is here now. And the other side of our line. So what has happened to our vertex? think about what has happened and why. Our vertex is no longer down here at the origin, 0, 0. It is now translated or shifted up 2 units. Why did it shift up 2 units? And if you're saying it's because of this 2 on the end, you're absolutely correct. And how do we know this is correct? We put some points in a graph, and we plugged them in, and so we know these points are correct. So couldn't we graph this much easier without having to do a table of values every time? So here's our vertex. Let's go ahead and write that in real quick. So our vertex is 0, 2. So you can start to see the pattern. If you know what the original parent function looks like, and we have a translation, then all we have to do is take the original parent function, cut it out, so to speak, and move it up 2 spots, and glue it back down. So let's try another situation here without a table of values. Let's say we now have x minus 2. Okay, well this minus 2 is our only translation to our parent function. Remember that our parent function used to go through 0, 0. So let's just say here's our parent function, which came through here, something like this, right? So I know that all I have to do is translate this down 2 units, right? We have a minus 2 here. So I could pick up this and I could move it, oh, maybe, and I could move this whole line down 2 right here. So I'm not going to try to move the purple line. I think it's stuck on there. But I'll draw another one that is 2 units down. So notice and compare, we have our parent function here in purple and our new line, which has just been translated down 2 units. So now our y-intercept is at 0, -2 instead of 0, 0. Okay, but notice if you look at these 2 lines, what do they look like to you? They should look parallel. And think about, do you know if they're parallel? How would you know if they're parallel? Well, if we take and we compare points, let's say this point here straight down to this point, we drop down 1, 2. If I pick another point, say right here, I should still drop down 1, 2. And any other point, let's just say here, 1, 2. So the distance between all my vertical points is consistently 2, so I know my lines are parallel, which means that the slopes are the same. We learned that. So basically, all that translation did is just pick this purple line up and drop it down 2. Didn't change the slope at all. Let's look now at what happens with our absolute value. Okay, so I went ahead and drew in our parent function. So what do you think is going to happen to this parent function? Well, if we look up here, minus 2, and based on what happened here in our linear equation, we can predict that this whole absolute value equation is going to pick up and drop down to the minus 2. So let's go ahead and draw that in, see what that would look like. So we'd come down here, move our vertex, our y-intercept down to the minus 2, and we would put a line in there, pretty close. And we could do from the other side as well. All right, so as good as we can draw, you can see if I looked at each of these lines independently, they look parallel. I could prove it by counting the distance between each of the 2 points, which is consistently 2. Okay, because I dropped down 2. And I can see it here too. There's 2, there's 2. So my sides of my absolute value v are parallel to my parent function. The only difference is that the vertex is now moved down from 0, 0 to 0, -2. Okay. So very easy to graph. Remember, our slope is just always up 1 over 1, up 1 over 1. There is no slope other than 1 over 1. So no change to the slope. It's just up 1 over 1. Okay, so let's continue on. Let's look at a different type of translation. So this is inside of our absolute value bars. So I would wonder, what is that going to do to my absolute value equation? And we can make some predictions. I look at this and say, well, this is inside here with x. It's not on the outside. But what's going to happen? So let's go ahead and use our standard points of -1, 0, 1 and plug those in. -1 plus 3 is 2. 0 plus 3 is 3, and 1 plus 3 is 4. Okay, so we have -1, 2 right here, 0, 3, and we have 1, 4. So I have a little bit of a problem here because I only have one of my lines, right? I haven't figured out my vertex, so I'm going to actually need to have some additional points. Well, the way my line is sloping here, I'm assuming it's going to head down and my vertex is going to be over here somewhere. So let's actually choose some more points. Let's go ahead and lengthen our table. So we'll put some more values over here. And let's choose a -2, a -3, and a -4. So a -2 plus 3 is just 1. -3 plus 3 is 0, and -4 plus 3 is -1, but we all know that just becomes +1. So we have -2, 1 here, we have -3, 0 here, and we have -4, 1 here. So now we can start to see our V, and that's what we're looking for because we know that absolute value equations, when they're graphed, they form a V. So with that in mind, let's go ahead and make our lines. Let's connect. We've got one there. And we've also got one to our left. Okay, so if you don't have the right points, that means you need to go back in and find some more. So what we're looking for, the key here is, what does this x plus 3 do? Well, look where our vertex is. Our vertex is no longer at 0, 0, but it didn't shift up or down. It actually shifted to the left. So our vertex is now at -3, 0. Our x value is -3, and we didn't shift up or down, so it's -3, 0. So what I'm wondering is, does that surprise you? Because this equation says x plus 3. Intuitively, you would think, well, it should shift to the right, but it doesn't. It shifts to the left. And if you think about what this is, we just found the x-intercept. If I was trying to solve for x up here and I have x plus 3, how would I figure out what the x-intercept is? I would have to subtract 3 from both sides, wouldn't I? In order to figure out that x is equal to -3. Okay, so we can do the same thing here. We have x minus 3, so let's go ahead and use some points. Okay, now again, I'm going to predict, since this one shifted to the left and it was a +3, I'm going to predict that this one is going to shift to the right. So I'm assuming that my V is going to be right here at 3, 0. So maybe I'll go ahead and choose 2, because I want to get a point on the left side of my vertex and one on the right side. I'm going to choose a 3, and I'm going to choose a 4. But again, if we chose the wrong points, we would just keep adding points until we saw our graph switch directions. So 2 minus 3 is -1, and the absolute value of that is just 1. 3 minus 3 is 0, and 4 minus 3 is 1. So if I were to graph this, I would have 2, 1 up here, 3, 0 is right where I thought, and 4, 1 is here. So in fact, if we draw a line, we can see that our graph did shift to the right. There we go. And make one more leg here. And there we go. So now we know that if we have a translation inside the absolute value marks, that's translating our x-intercept. So that goes left or right. If we have one on the outside, that's translating our y-intercept, so that is going to go up or down. Let's put it all together. So the easiest way to do this is to, 1, look at our translations and write our vertex down. Well, in this first one, we have an x translation of +3. So we know it shifts the opposite direction. Our y-intercept is translated -2, and that is accurate. We do actually go down -2. So I'll go ahead and put my vertex at -3, -2, and then I know my slope is just going to be up 1 over 1, up 1 over 1. I don't need to make a table of values because I know the pattern. So I can just plot a few points and draw my line. Okay, moving on to our last one then. I know my vertex on this one is going to be opposite of what's inside the absolute value, so +3 and -2. So my x-intercept is at 3 and my y-intercept is at -2. So the combination of those gives us our vertex. And then again, our slope is just up 1 over 1, up 1 over 1. We know that both sides of these are going to be symmetric. And there's the graph. No table of values, no long computations. I merely graphed it by looking at the translations, the shift left and right, and the shift up and down. And that concludes our lesson for today.